Give you a quick little example, so here's this huge Thevenin trick. Okay, if you like, you can call it a Thevenin hack, if you will. But so let's say, for example, I have some funky device. Let's say some funky device F, and then let's say F is connected to some arbitrary network. Okay, I'm just sitting here and drawing out something, some arbitrary network. But remember, it's a linear network. Okay, I can keep going like this. Okay, I can just go on and so on. So I have some arbitrary funky network that is connecting this my device F. Okay, what this trick says is that I can cut this device out here. Okay, and let's say I place the device F here. Okay, so that's the cut piece of the device that I've placed on the right hand side. I can take the rest of the network and replace that entire network with its Thevenin equivalent for the purposes of analyzing that device. Okay, so the voltage V and R and these two will be equivalent to the extent that I want to figure out properties of the device F. Okay, this is absolutely amazing. So whenever you see funky little devices, whether it's nonlinear devices or we'll see some other very interesting devices later on in this course, what you can do is isolate that device and replace the rest of the network with a Thevenin equivalent if that network is linear. Now you can do the same thing, and in some cases it may be preferable to replace the rest of the circuit with a Norton network. Okay, either way is fine. You can do a Norton or a Thevenin, and the two are equivalent. All right, I think with that we are ready to start talking about the analytical method for analyzing nonlinear circuits. So we will start with the basic circuit that we have here on the right-hand side, which is my Thevenin equivalent with the voltage and resistor in series connected to the device D. Notice I've gone ahead and drawn the first few steps of doing the node method. I've added a ground node and I've labeled the two nodes of the circuit with VD, the voltage across the device, the funky device, and also labeled the voltage at the terminal at the node between the resistor and the voltage source. All right, so what I'm going to do now is start with applying the node method to this device and then see how we can go ahead and analyze it. Okay, as before, the device equation is ID equals A raised to BVD, where A and B are some constants. Okay, let's get started. So let's go ahead and write the node method for this device. And remember again, the node method applies for linear or nonlinear circuits. Once we are in the ECS playground, you can go ahead and apply the node method, which derives directly from the KVL/KCL method. Okay, so there's just one node here, the node with voltage VD, and let me go ahead and write the node equation for that node. Let me sum the currents leaving the node, and so the current leaving in the left-hand direction is simply given by VD minus capital V divided by R. And I summed the current going out of the node going downwards, and that is plus ID equals 0, where according to the node method, I replace ID with the expression, the device relation for the current ID given by A raised to B, A raised to, let me do this again here, but ID equals AE raised to B VD, okay, where A and B are constants. So that is my node equation. And just for fun, to show you a variety of methods of solving nonlinear circuits, let me not substitute the device equation into the node equation right away. Let me leave it explicitly outside for now. Let me label this as equation 1, and let me label this as equation 2. Equation 2 is simply the device equation, and which is same as the equation here. And equation 1 is the node equation. Okay, so what do you see here? So you see two equations, 1 and 2. So you see two unknowns. Okay, and I have two equations. Okay, so I should be able to solve this. But notice my second equation is nonlinear. It is not a linear equation, and so therefore I can't use some of the simple ideas of solving simultaneous equations. I have to go with some more sophisticated methods. Okay, so there are a couple of ways in which you can solve this in our analytical method. Okay, we'll look at other graphical and other techniques later, but in an analytical method, I would like to solve this by one of two approaches. I can use trial and error, or I can use a variety of numerical techniques. So again, 6002X is not about how to solve nonlinear equations, so don't worry about that. Just suffice it to say that once you have these two equations, we somehow need to solve them, and 6002 is not about solving nonlinear equations, so don't worry about how to do it. I'll show you a couple of methods, but you really will not be responsible for solving nonlinear equations in general. So let's look at a couple of techniques. As I said, one method is by trial and error, and another method is you employ various numerical techniques. And I'll show you one approach to doing that.